Good afternoon, everyone. Welcome to the CCOM-OE seminar. Today, we're very lucky to have Dr. Chris-Lai here with us. Dr. Lai is an assistant professor in the School of Civil and Environmental Engineering at Georgia Tech. Before joining Georgia Tech in November 2019, he worked for 3 years as a postdoctoral research associate of the Extreme Fluids team at the Los Alamos National Laboratory in New Mexico. He was awarded his PhD degree in 2015 from Texas A&M University and his Master of Philosophy and Bachelor of Engineering degrees in 2010 and 2007 from the University of Hong Kong, all in civil engineering. His research interests are in the broad areas of environmental fluid mechanics and experimental fluid mechanics. Currently, his group focuses on multi-phase flow turbulence and heat and mass transfer across a melting ice surface. So we ask that everyone please hold their questions until the end. And Dr. Lai, you are able to share your screen.
Okay, thank you, Nicole, for the good introduction. Let me share my screen. Okay, can you all see my screen well?
Yes.
Okay, thank you. So let me first start by thanking Nicole for organizing this seminar. It is a very smooth process, and also thank you, Tracy Mandel, for inviting me to give a seminar here. I'm happy it's my pleasure, and I'm happy that my work has interest to you guys. So a little bit about myself. I'm an experimentalist, and most of my work done small-scale experiments in the lab, and what I'm interested in is turbulent mixing and turbulent transfer of in environmental flow. And today, one topic that I think would interest you, and that is related to natural gas ships in the ocean. And what I want to show here is the flow field generated by this rising methane bubbles. If you want to model it, you cannot model it with the usual classical integral plume analysis with an entrainment hypothesis. And we have and we'll show you why, and we'll propose a unified framework that will bridge the classical entrainment strong plume to this weak bubble plume that I will define here today. So first, I would like to say a few things to thank my colleagues. The work that I'm going to present today is in the first paper here about 2 years ago in 2019, and that work is done between myself with Scott Skolowski at A&M, Texas A&M, and then Bin Wang, who is now at assistant professor at University of Missouri. If I had time left, I would like to discuss a very recent work that is recently accepted in Experiments and Fluids on how we can get volumetric time resolved fluid data in the lab using just only planar data. So this is kind of the plan for today. So turbulent jets and plumes are ubiquitous in GFD flows and in engineering applications. And here are some examples here. You have this volcanic eruption plume. It brings up a lot of different gases, particulates up into the air, and if it is stratified, it would stably spread out in the neutral buoyancy level. And what you want to know here from an environmental protection perspective is one gas that is pushed up in the atmosphere is sulfur dioxide, and then you want to know where that sulfur dioxide is going. You need to predict what is the input mass flow rate of this sulfur dioxide of this volcanic eruption plume. And so that's what you want to know with a plume. If you work with wastewater disposal, treated wastewater is usually released back to the ocean via outfall system. And this is a picture in the Adelaide outfall in Australia, where you have this treated wastewater jet coming out into the ocean, and then you can see the scaling with respect to the diver here. And other situation where you would see a plumes in action is something that I'm working on now, is related to subglacial freshwater plumes that is released at the base of terrestrial ice, and because it is fresher, it tries to rise along the interface of ice and water. And because it's turbulent, it's going to mediate the melting rate of this ice interface. So in all these different cases, you have a turbulent jet plumes flow field, and we want to know what is the volume flux, what would be the trap height, and what are the dilution. And very often, these quantities become the output, become the input of a larger scale model that would track the mass transport in the regional and global scale. So classically, how would you incorporate these small scale processes into large scale oceanic model, which do not resolve this flow? You would bridge it with the integral models that is first proposed in Morton, Taylor, and Turner, 1956. And what I've shown here on the left is a very simple schematic setup of a simple pure plume, so a pure source of buoyancy from a source, and it will spread out and then create a mean upward flow W. And then the buoyancy profile is going to spread out as well. And then they will look like a Gaussian shape in a time mean quantity. So as I said, what you want to do here is you want to predict the evolution of this plume, and that boils down to you want to know what is the volumetric flow rate, what will be the momentum of this plume at different Z locations away from the point source. And Morton, Taylor, and Turner help us do that. And what we have is the integral plume formulation, which is written down here for the simple plume, and where the background has no density stratification. So this is that. And for you to close this problem, there are two parameters that you need. I will talk about first the simple lambda in green, which is the ratio of the spreading width of the buoyancy profile to the mean velocity. And you can, from experiments, we know that it's between about 1.1 to 1.2. So you can find from experiments and then you specify it. So that's done. But the key thing about this modeling is the entrainment hypothesis. And it tells you how the volumetric flow rate of a plume would change with distance. And the hypothesis basically tells you that the entrainment rate is a certain fraction of the local centerline velocity, and that fraction is expressed by this entrainment coefficient alpha. So from experiments, we know for pure plumes, this alpha is on the order of 0.1. And in fact, this value, this constant value, is used in a lot of modeling of plume, like volcanic eruptions, buoyant jets, or fire plumes. But implicit to this entrainment hypothesis is that it implied the spreading rate of this plume is going to be linear with height. So the BG symbol here is the local plume width. I hope you can see my arrow here, and then it has to be linear with the vertical height, and that is implicit inside this entrainment hypothesis. And yeah, that's that. So when people try to plot this, adapt this approach, integral approach, initially developed for a single phase flow back in 1956. And adapt that to a two-phase plume, we notice the following. In a single-phase plume, the buoyancy is due to the dissolved active scalar, so like heat or salinity. And the buoyancy profile is continuous across the plume cross-section. But when you move to a two-phase plume, you can think of the buoyancy being generated by gas bubbles or by heavy particles like sand falling through the water. The buoyancy is due to the drag exerted on the surrounding water by the dispersed phase. And because the dispersed phase, they are discrete in nature, the buoyancy profile is discontinuous. But if the dispersed phase concentration, or you can think of the volume fraction is high, there would be the individual wicks behind the particles will interact, and what it would amount to, it would spread out the buoyancy profile and make it approximately continuous. And this is this explain, or at least provide the basis of why you can use the originally single-phased integral plume formulation to a two-phase flow and being used so widely in modeling. And one of that example is, of course, the oil spill modeling by my advisor Scott Sokolowski at A&M, or by Pujiyaba at University of Clarkson. Okay, using the integral approach for two-phase jets and plumes. But a new scenario would arise when your dispersed phase concentration or void fraction are actually very low. And here I'm showing you an example of that, which is the natural methane gas seep on the ocean floor. So this is a in situ photo of the gas seep in Gulf of Mexico taken by Wang et al. 2016. And what you're looking here is you're looking at the hydrothermal vent where you have this methane gas bubble rising up. And in this experiment, what we did was we put down ROV and put down a stereoscopic imaging system to take pictures of the rising methane bubbles. And you can see in this grayscale image here. And from image processing, we figure out that the gas inflow rate is on the order of 0.01 to 0.23 normal liters per minute. So they're very low. And if you look at just the pictures here, you can see that they're quite spread out. And this makes us to think, are the wicks of the individual bubbles interact enough so that you have a more or less continuous buoyancy profile? And if that is not the case, so if the bubble are quite far apart from each other and they don't work collectively, how would that change the induced flow? How would that change the plume volume flux as it rise along the water column? So this is our question. And for a bubble plume, there is an important dynamic scale that characterizes its behavior as a function of the distance. And that dynamic length scale is called D, and is proposed by Bombardelli in 2007. And it is basically a ratio of the buoyancy force relative to the slip velocity or the momentum of the dispersed phase, given as such. And the idea here is by Bombardelli is if you normalize your vertical height with this dynamic length scale D, there are two distinct phases that you can expect. So if Z over D is less than 5, you have the classical plume or strong plume that we just discussed. But then the flow behavior would depend on the initial condition. So it would matter whether your inflow of gas is distributed over an area, over a large area, or is it concentrated at like a point. So it would depend on the initial conditions. But once you move away from about 5, you will be in the asymptotic phase, and all plumes should behave the same, and they would forget about their initial conditions. Now, with this framework, we expect that our natural gas seep, which we define as a weak plume, should appear when this ratio Z over D is large. And intuitively, you can think about like this is, as you go higher up in the water column, the gas bubble will spread out more and more. And there will be a point where they will cease to interact with each other and will rise individually. And this is the region where the buoyancy profile would become discontinuous, because each bubbles would act like a point momentum source in the flow field. Okay. So to test this hypothesis, we turn to our wave basin at Texas A&M, and this is a pictures showing you that. So on the left-hand side is a overview where we have this wave basin, and our experiments is actually done inside this dip pit, shown or circled in red on the right-hand figure. And this pit is having a horizontal dimension about 4.6 meters to 9 meters, but then it's very deep. It is in the next slide, you will see here the vertical cross-section view. So in this dip pit, the total height is about 16.8 meters. And then the cross-section, as I mentioned, is 4.6 by 9.1 meters. And what we do there is, the concept is this: at the bottom of the pit, we inject a very low flow rate of air into this wave basin. And then what we do is we inject a gas flow rate of air at a constant flow rate, and then we build this 3D cage system so that we can put in our imaging system to measure the bubble size distributions, the plume width, and also measure the liquid phase velocity using an acoustic Doppler velocimeter by Nortec. And we are measuring this, the behavior of this bubble plume from very close to the source all the way up to near the water surface, so about 60 meters away from the origin. And we consider two injection flow rate, and they are 0.25 and 1.2 milliliters per minute. And we do these experiments and measure the plume flow properties. One thing I'll mention here is that in this wave basin, the water is very clear. And for us to get a good signal for the ADV, we make this ADV seeding particle feeder that is placed in the area where we would find the bubble plume, and then we inject seeding particles to the region of measurement so that we can get a strong velocity signal. And with our analysis, we find that the secondary current generated by this feeder is negligible and will not affect the dynamics of the rising plume. Okay, so a couple of images here. The two flow rates in the left-hand and right-hand figures. And these are not rectified, just image, but after rectification, we can traverse the 3D location of the bubbles and find out its equivalent diameter. So the median diameter of this two flow rate is about 4 millimeters. And then the slip velocity or terminal velocity from correlation before, we know that this is about 22 cm per second in our flow field. So let us take a look at the mean liquid velocity and void volume fraction. And these are shown in the left-hand and right-hand figure. First, in this case, even if such a low gas flow rate, we see that the mean velocity and then the mean volume fraction, they follow a Gaussian distribution, just as the classic plumes that we looked at the beginning of this talk. And I want to bring your attention to this BG and BX. They are the local plume width, where the local velocity or void fraction decreased to about 37% of the centerline value. So they characterize the local spread of the plume as a function of Z. And if you look at the ratio of the void fraction profile to the momentum, which is the mean velocity, they are on the order of 0.7. And for two-phase flow, it is a common observation that the dispersed phase is spreading slower than the single-phased momentum. And this is contrary to a single-phased jets and plumes, where the reverse happened, where the spread of mass and temperature is actually faster than a single-phase flow. So this is a characteristic of a two-phase system. And the value of 0.7 found here is in agreement with published data. Okay. Now, if you plot the BG and BX as a function of the vertical distance, this is where we see a drastic difference with the linear spread. So on the left-hand side, what we have shown here is the BG and BX for a two-flow rate. They're in different colors. But then if you compare it to this dashed line here, which is the linear growth required by a strong plume, by the entrainment hypothesis, you will see that for the weak bubble plume that we have here, the spread is much slower. So this is the first observation. If you plot the same data on a log scale so that we can review the power law dependence of the spread with Z, we observe that except for the first data point, which is closest to the source, I think I remember this about 1 meter above the source, the rest of all the other data points increases as the square root of the vertical height. And this is clearly different from a linear spread demanded by the entrainment hypothesis. And that makes us think that maybe the entrainment hypothesis is not valid. And this is an important observation, because that could mean that you cannot just use the usual integral model to predict the volume flux, or in general, the behavior of a weak bubble plume. Now, let us look at another comparison. So here we are showing you the centerline velocity decay of the liquid velocity with height. And in the figure here, this is a collection of data spanning a wide range of Z over D values, almost over 4 orders of magnitude. And what you see here is that the weak bubble plumes in red, they are clustering in their own range in the large Z over D range. And then the strong plumes, the classical plumes, they cluster around Z over D in the smaller size, so less than about 10. And what you see is that they have different scaling behavior. For the classical plume, it obeys the well-known -1/3 power law. But for the weak bubble plume, it changes to a steeper slope, to a -1/2. And this behavior, quite coincidentally, was predicted by Bombardelli's semi-analytical curve. And it was quite surprising, because when Bombardelli did his semi-analytical prediction, he was only thinking about the strong plumes. So he worked with the governing equations, make the entrainment hypothesis, and then solve the equations. But then the prediction of the centerline velocity decay actually predicted that for large Z over D, you do have this -1/2 scaling. So that was quite interesting, because this shouldn't have been predicted by the entrainment hypothesis. So one interpretation of that could be when the bubble actually spread out more and more, it actually can reflect to a certain degree the weakening of the interacting wicks, or this discontinuous buoyancy profile. Okay. So let us look at a little bit of analysis. So On the left-hand side, we have a usual strong plume, classical plume. We know that the jet spread as the dBg/dz is equal to constant. It doesn't depend on the vertical height. But for weak bubble plume, because we observe that the width is spreading out to the square root of z, it makes us think that it should obey a diffusive process, a turbulent diffusion process. So we start out by trying to write down a turbulent diffusion process for the Bg squared, which is the variance. And this is in time, but we have a steady flow so that you can transform time into space, and then write the variance change with z in this form of the equation. And ultimately what you get, you can solve for Bg and Bx, and this is the formula. And from the data, we can quantify what are the turbulent diffusion coefficients for Bg and Bx. And then this is what we've done in this slide. And a couple things here. You got the data for the two flow rates Q1 and Q2, and the data in this green box highlighted here is the data fit, or the estimate of EG and EX from the measured data of the plume width. And they are on the order of about 50 to 100 times 10 to the minus 6 meters squared per second. So this is the data. Now we want to think about what could have caused this apparent diffusion coefficient. And there are two possible candidates. First one is turbulent diffusion, because the bubbles, they're large, and the wicks behind them, they're turbulent. So they could have spread by turbulent diffusion. And and then we know that the turbulent diffusion coefficient should scale with the square of the UIMS, of the fluctuating velocity, and then times the integral time scale. So this is one candidate. Or the spreading can be actually due to the wobbling effect or wobbling trajectory of the bubbles. And for the 4 millimeters gas bubbles that we are talking about here, it is in the wobbling regime. So you follow a helical path, and the shape of the bubbles are ellipsoidal. And because of this helical path, it can cause the spreading. And you can quantify that spreading with a diffusion coefficient that is equal to the product of this lateral excursion. So the mean lateral excursion of those bubble trajectory times the lateral excursion velocity, UE. And what we find that is the second mechanism, the bubble lateral excursion, is actually giving us value much closer to the data fit of ET, of the ET. The turbulent diffusion is actually an order of magnitude smaller than the fitted value of ET. And this evidence point to us that is actually the helical path of the bubbles that is causing the spread of the plume. So, with that understanding, we now want to look at how we can predict the evolution of the volume flux of this big bubble plume. And again, here I'm contrasting the different behavior. So on the left-hand side, we have the classic strong plume, and we know that the volume flux should increase as a power law with Z, and that is set to the power minus set to the power 5/3. And if you take a derivative of that, so dq dz is the incremental entrainment, and you will see that that is proportional to Z 2/3. And what that means is that as for the classical strong plume, the entrainment is getting stronger as it travels up the water column. But this behavior is completely different for the weak plumes. We have shown that the volume flux for the weak plumes actually only increase with the square root of Z, so it's slower than a classical plume. And then dq/dz, because of this formula, is actually scaling with the -1/2 of z. So as you're moving up, it is entering. You can think of the entrainment power is getting slower, smaller and smaller. And we think that this makes intuitive sense because as your bubbles become so spread out, they cannot work collectively together. They won't create an entrained flow into each other. So your dq/dz should weakens with height. Now, can we define an apparent entrainment coefficient for weak bubble plumes? And we are doing this solely because we want to see can we treat or predict the weak bubble plume behavior with the usual entrainment formulation just by tweaking the alpha, okay? But as I explained before, you cannot do that because the entrainment formulations premeditate or implied that the growth of BG has to be linear, which is not the case for the weak bubble plume. But nonetheless, let's try this route. Okay, so on the top path, we see the equation for strong plumes, and we know that for pure plumes, the alpha is about 0.1. For weak bubble plume, the dq/dz is given by this formula, and if now you try to match between of this expression between the strong and the weak plumes, you can define what is called the apparent entrainment coefficient, which I denoted as alpha subscript WP here. WP means weak bubble plume. And from this, it tells you that the weak bubble plume or apparent entrainment coefficient should scale with z -1/2. So we want to use our data to see if we can recover this z equals 1/2 scaling. And how we do that is we take the second expression here, so we can calculate the dq/dz between two different vertical elevations, and then use the formula to back calculate what would be the apparent entrainment coefficient. And this is the result, also appearing in the poster of my talk. So what you're seeing here is the entrainment coefficient as a function of the normalized vertical height, z over d. So for strong plumes, there are some variations, but they are on the order of about 0.1. The variation being that as your z goes higher, there's a tendency for it to drop, but then it is on the ballpark about 0.1. But for the weak bubble plume, it is at the bottom part here. You notice that the apparent entrainment coefficient is actually much smaller than the 0.1 value. The second observation is, if you look at the scaling of these red data symbols, they are actually fitted quite well by a z -1/2 scaling. Okay, so our data actually supports this z -1/2 scaling for the apparent entrainment coefficient. Okay, and again, then I've alluded this a little bit earlier. Can we just forget about the fundamental difference between a weak bubble plume and the classic plume, and just take the apparent entrainment coefficient and plug it into the same formulation and say problem solved? No, because the entrainment coefficient, entrainment hypothesis implied a linear growth, which for a weak bubble plume is not. And to be more precise, what that means is that if you used a reduced entrainment coefficient in the usual formulation, you would get the velocity right, but the plume width would not be right, and because in a weak bubble plume is spreading much slower than a strong plume, and that means that your Q, your volume flux flow rate will be in great error. So with the data set that we have, and also combining with the published data set we can find for a strong plume, we propose a unified scaling framework to bridge these strong weak plume transition. Yes. So here we are showing you a plot of the plume width, the BG, and on the right-hand side we are showing you the asymptotic relationship. But if you do a curve fit to both regime, which is represented by this dark line here, you can see it will fit the data well. In this fitting process, in the weak plume, the additional parameter that is needed is a non-dimensional turbulent diffusion coefficient. And we find that this value is about 0.01 in our study. And we also try different ET, and this is shown here, and the value of 0.01 will fit the data well. If you want to predict the volume flux, these are the formula. And again, if you look at the weak bubble plume region here, which are the red symbol, the non-dimensional turbulent diffusion coefficient of 0.01 will also fit the data reasonably well. If you want to look at the momentum, this is the scaling law here. The non-dimensional diffusion coefficient of 0.01 also would fit the data quite well. I want to point out here is quite interesting to see that from the prediction, the momentum flux of a weak bubble plume would actually become a constant with height. And I think this is a reflection of the fact that the bubbles themselves, they are so far apart such that they are collected, such that the buoyancy impact on this wide plume is very small. So it's not accelerating the flow anymore. So your momentum flux becomes approach a constant. Okay. So conclusions here, I think I will just leave this here as a lead, or as a lead to invite questions and discussion. So I think it's almost time to. So I will end my talk here, and thank you for your attention. I will take any questions that you have.
Thank you so much, Dr. Lai. That was an excellent presentation. As usual, if anyone would like to ask Dr. Lai a question, you can feel free to either enter it into the chat and I'll read it aloud, or you can unmute yourself and ask Dr. Lai directly.
Well, I was excited to see the new experiments in fluids paper. So if no one else has questions, then I'd be curious if you have any slides about the sort of three-dimensional volumetric.
Right. So that is a work that is accepted, and what we're trying to do there is we're trying to solve the problem of how we can get 3D data out of 2D data. And as an experimentalist, I'm sure, Tracy, you know that's important. You always want to get 3D data. And kind of the reason why we want to do that is if you now want to do a volumetric measurement of the velocity density field, you need a lot of cameras. And a basic calculation or basic tally will tell you that you need 12 cameras to do the job. And in the experimental fluids paper, what we are saying that we can do the same job with only 3 cameras. So this is a huge cost saving for the experimentalists working in the lab. So so kind of let me just run through quickly the data that we have here. So this is a data set that we took in a wind tunnel. So you have a jet going down through a cross section, And this cross section is taking measurement at the center plane, at the cross section of the jet. So you take the velocity, you have the concentration measurement, and then this is a time resolved measurement, and then this is the data shown on the right. So the color map showed you the relative concentration, and then you got the velocity fields. And our goal is to turn this planar data into volumetric measurement so that you can see the density structures and then also see the turbulent flow itself. So this is the goal. I will skip the math here, but in a nutshell, what we are doing is we take the measurement data as the initial conditions to solve the Navier-Stokes equation. That is the idea. You take the initial data to solve the Navier-Stokes equation and basically solve the Lagrangian form of the Navier-Stokes equation. So we do that, and what it entails, actually the concept originates back to G.I. Taylor's Frozen Cloud Turbulence in 1938. But then the improvement here is that in G.I. Taylor's work, he said that, well, the affection velocity of the turbulent eddies is the mean flow. But we say that, no, we just use the full velocity to affect the flow. And this is how we achieve a great accuracy of the reconstruction. So, and for validation, what we did was we went to a turbulent channel flow DNS data set, and we take a plane, and then we'll only have the plane data and reconstruct the volume. So, and this is the comparison. So we actually look at two locations. We look at the centerline location where basically you have a kind of homogeneous isotropic turbulence flow field. But what is more challenging is the near wall flow, where you have a lot of shear. And I will just skip to the near wall flow. And what I'm showing you here is the induced turbulence structures of the volumetric data. And on the first column is the DNS data, is the exact solution. And the second column is what Taylor would give you. And in the third and the fourth is what our method would give you. And there are two variants of our method that is related to how we treat the path line, but I won't go into detail. But if you compare that, what you will see is our method reconstruct the turbulence more accurately than what Taylor can. Because if you look at what Taylor have here and compare to the DNS, it basically smooth out the turbulent flow and also move the structures to a not correct position. And this is not the case when you use the instantaneous velocity. So this is a point-wise comparison. And I will just say here is the reconstructed volume that we can have is on par with actual tomographic PIV. And then we compare to the DNS data, we achieve accuracy better than 10%, or error better than 10%. And so that's validation. If you apply that to the jet flow that we have, this is a rendition of the iso contours of the density structures and also the turbulent eddies. But it would be most revealing if you look at this video, and it's the same data. And what I want to emphasize here is if you look on the left-hand figure where the red tube-like structure are the turbulence, are the swirling motion, and the blue cut planes, they're showing you the highly dissipative region. And only by solving the Navier-Stokes with a full velocity vector could you retain the thin structure of this highly dissipative region. And this is a known feature of turbulence, is the highly dissipative region, they are thin sheets. And if you go with Taylor, you will flatten out this sheet and you cannot make them thin. So that's one thing. The second thing, is the problem that we solved is now you're looking at from the top, and if you focused on any of the red structures to your in the left animation, you will see that the structures can actually deform, break, and coalesce, and that is what you would expect in a turbulent flow. You will not be able to do that with Taylor. So this is a really quick snapshot. really quick snapshot of what we have. So this is now accepted. I think the next step, what my collaborator and I are doing, is trying to extend this to a two-phase flow. It's an even more challenging case where you can think of a sediment or bubble. They are blocking you the liquid flow. So in your plane, you have region where it corresponds to the air. It is not part of the liquid, and you have data gaps. So how do you reconstruct the fluid flow field with data gaps? And again, this is about how you solve the Navier-Stokes equation. And what we're thinking of, we have to add the surface tension force. And by measuring with some technique, you can measure the interface, and there's a model for how you can incorporate the surface tension force. Basically, you just need to find out what is the curvature of the interface, and you can solve that. So we're working on that, and hopefully, next time if I come back, I can present that work. And we believe that if that is successful, it will be a good addition to the experimental community doing two-phase flow, because you can have 3D data. So thank you, Tracy, for that question.
Yeah, thank you so much. That's really cool.
Great. Does anyone else have any other questions? All right. If not, thank you again, Dr. Lai. That was a really excellent presentation. Very interesting to watch. And also thank you for the virtual visit earlier as well. I think that was very beneficial for all the parties around. So I just want to remind everyone that we are off next Friday. So we will not have another seminar until March 26th, where we will have Dr. Brian Bingham from the Naval Postgraduate School. So thank you again, Dr. Lai, and everyone have a great weekend.
Thank you, Nicole. Thank you, Tracy. Have a great weekend.
Thanks for joining us.
Yeah, thanks.